Okay, welcome to the second episode of the electricity and magnetism topic. And in this flip lesson, we're going to look at the motion of charged particles in electric fields. Let's get into it. So to start off with, we're going to talk about the concept of electric potential difference, otherwise known as voltage, which really relates to the amount of energy that a charge has in an electric field. Now, really, this first slide pretty much, it comes straight out of my Year 11 notes. If you've done Year 11 with me, you probably would have seen this stuff before. Hopefully, if you've done Year 11 elsewhere, it's not completely new to you. But let's just talk about potential difference, and let's start by talking about potential and energy first. And before we can talk about energy, we really need to talk about the concept of work. So, almost takes us back to Year 10, but when an applied force causes an object to move, work is done. So if we're just pushing on something and it's not moving, we're applying a force. It's only when we apply a force and cause something to move that we are doing work. The amount of work done, given the symbol W, is equal to the product of the force applied and the displacement or the distance travelled of the object. So work equals force times displacement, and sometimes you see that written work equals force times distance. Energy is defined as the capacity to do work. Basically, energy and work are in a sense the same thing. They have the same units, they're measuring the same thing. Let's elaborate a bit. The energy gained by an object is equal to the work done on it, or the energy lost by an object is equal to the work it does. So if work is done on an object, it will gain energy, it'll gain the capacity to do some more work, or if an object does work, it will lose energy and work will be done. Any charge placed in an electric field has electric potential energy, just like any mass placed in a gravitational field has gravitational potential energy. So if we hold a ball up above the ground, that is said to have gravitational potential energy. It has the potential to do work as soon as we let it go. As soon as we let it go, gravity will cause it to accelerate. Because it's accelerating, it will have velocity. If it hits something, it'll have the ability to exert a force on it and cause it to move. So it has the ability to do work. So we can say it has potential energy. If we think now about two charges in an electric field, if we place about a charge in an electric field, it's either going to be attracted or repelled by the other charge or by the electric field, and therefore it has potential energy. It has the potential to move. If it has the potential to move, it has the potential to have energy or gain energy. If it has energy, it has the energy capacity to cause something else to move, therefore to do work. So we can think a little bit of voltage being like gravitational potential energy. You may have heard me talk about the analogy to a waterfall. Voltage in an electric circuit is a bit like talking about the height of a waterfall. The higher a waterfall is, the more energy the water will have when it reaches the bottom as it flows over that waterfall. The higher the potential energy, the gravitational potential, it's a bit like the higher the electric potential energy. So mathematically, how do we sort of express what we've just said here in a more rigorous mathematical, at a Year 12 level, let's say? So mathematically, electric potential difference, which we give the symbol delta V, or voltage, so delta is just that upside down triangle, is defined as the work done per unit charge in moving a charge between 2 points, and that's 2 points in an electric field. So voltage is equal to work done per charge. It is the work per charge. Whenever we divide, we say per. Something is basically something divided by something. So voltage, symbol delta V, has the units volts, and we use V for volts. I've got this down here, I'll jump to that now. Voltage is given the symbol delta V and is measured in the units of volts. That can be a little bit confusing. If we talk about time, it has the symbol T and it's measured in units of seconds, which has the letter S. If we talk about length, it often has the symbol L and it's measured, or displacement in terms of physics, S, and it's measured in units of meters, which has the symbol M. But here we have the same letter for both. So just don't let all the V's confuse you. It's volts is the unit, voltage or electric potential difference is the unit. W is work done, Q is the charge. Probably should have had a lower Q here. I think that auto-corrected because it was at the start of a line, but it's not such a bad thing because often in questions they will use a capital Q or a lowercase q for charge. So you'll see both of those used. So in simple terms, voltage indicates the energy of the charge that is flowing. High voltage indicates high energy and low voltage indicates low energy. So high voltage, the charge that's moving has a high amount of energy. Low voltage has a low amount of energy. The voltage of a charged particle moving through a 240 volt main circuit is much higher, so that those charges will have much more energy than the charges coming from a 1.5 volt battery in the remote control of your television or something like that. So that is voltage. Let's keep moving. So the next thing we need to know about is the electron volt. So we've got our science understandings here from the SACE board. The electron volt is the work done when an electron moves through a potential difference of 1 volt. It's actually a measure of energy. If you move an electron, let me write this out, an electron, if we go back to that formula we just used, which says that delta V equals work done per unit charge. So if we rearrange that, we get work done equals delta V times Q. So if we have an electron and we go 1 volt times by the charge on an electron, 1.6 times 10 to the minus 19 coulombs, that gives us 1.6 times 10 to the minus 19 joules, and we refer that to that as an electron volt because it's a very common unit of energy that we use in physics. You would have used that probably last year in the radioactivity topic when we talked about how much energy particles from like beta decay and alpha decay and gamma decay and all that sort of thing have. So if you need to, as it says here, convert energy from joules into electron volts and vice versa, if you want to go from electron volts to joules, you times by 1.6 times 10 to the minus 19. If you want to go from joules to electron volts, you divide by 1.6 times 10 to the minus 19. The next thing that we need to just look at is, go back and look at, is electric field strength. But this time, in terms of not looking at it in terms of Q, as in the last topic we introduced the concept of, we introduced the concept of electric field strength and said it was defined as the force per unit charge. But now we want to define it in terms of the voltage. So if we have, and generally we deal with cases where we have 2 parallel plates. If we have 2 parallel plates, one negatively charged and one positively charged, and we have a voltage applied between those 2 plates. And if you remember the electric field strength between those 2 plates from the last topic, we're going to get a uniform electric field. We won't worry about the edge effects where it sort of bulges. It's the direction of a positive charge, so it would go up. And if we want to know the electric field strength anywhere there, we work it out by, actually I'll just add one more thing to that. These are separated by a distance d. We can use this formula here, E equals delta V on D, to work out the electric field strength. If you want to think about why is it uniform, well, if say we had a charge up here, let's say it was positive. Actually, let's just write that differently. A positive charge up here, it's going to be getting attracted towards the negative plate, and it's going to be being repelled from the positive plate. Actually, I'll do those arrows differently. Now up here, because it's closer to the negative plate, there's going to be a greater attraction and the repulsion here will be less. But if the positive charge had been down here, the repulsion from this plate would be greater and the attraction would be less up to here. But the net effect is the electric field strength will be the same at any point in that region between two parallel plates. And if we know the voltage between the plates, we can use this formula here, electric field strength equals delta V on D, to work out the electric field strength. Okay, let's continue. So if we know the electric field strength between two parallel plates or within an electric field, the electric field strength, the next thing we want to do is work out the amount of force that a charge experiences, and therefore if we work out the amount of force that it experiences, that we can work out the acceleration of a charged particle in an electric field. So the formula, which you are given on your formula sheet, but we do need to know how to derive this formula for the acceleration of a charged object in an electric field with a certain mass is given by this formula. And to derive this formula, it is fairly straightforward. We know, what colour shall we use? Blue? Yep. We know that from the definition of electric field strength, that electric field is equal to force per unit charge. And we can rearrange that a formula to get that in terms of force. So the force that a charge experiences due to an electric field is given by EQ. And we know also from Newton's second law that force is equal to mass times acceleration. So we've got to justify how we equate these two things to do this derivation. So the force that will cause acceleration must be due to the electric field Therefore, we can say that EQ must be equal to MA, and then if we rearrange that by basically just dividing both sides by M to get rid of the M's there, we get left with basically this relationship here, that acceleration is equal to EQ on M, or QE on as M, as it is written there. So hopefully that's a fairly straightforward definition. So we'll just talk now about an example where we would use that, and that would be in the example of something like the Teltron tube, which I've got pictures of here and I've demonstrated to some extent at least in class hopefully. So in a Teltron tube, down here we have a little filament. You can see the light in this one here is this filament. As that gets hot, there's electrons, basically free electrons at the surface. here, which you can't really see at the end of this, where there is a lead going on there, but you can't really see it. There is a positively charged plate that has a narrow slit in it. We apply a higher voltage there, and that will cause the electrons to be accelerated. So this will be positively charged, the electron is negatively charged. It'll be accelerated through this field towards this plate, and then some of the electrons can get out through this beam, and then they come out and they strike this phosphor screen, and we can just see this little purple trace where they strike this screen so that we are able to see them. Now, if we want to work out the initial velocity of those electrons, we can do that using basically that the work done on those electrons will be equal to Q times delta V, which is going to, better put the V in, which is going to be equal to their kinetic energy. And then we know that kinetic energy is equal to a half mv squared. So we can basically, if we know the kinetic energy and we know the mass of the particle and we know the mass of an electron, we can rearrange that formula and we could calculate the velocity of those electrons. I won't do that right now, but I'd hope at year 12 that you would be able to do that. Now, when this electron moves into this uniform field, it's very much going to be like the case of horizontally throwing a projectile, but rather than gravity being the force that acts on it, the electric field is going to provide the force. Now, because this electron is negatively charged, it will be anti-parallel to the electric field, which basically just means instead of going up, it'll go down. I just think of it, you've got a negatively charged electron, it will be attracted to the positive plate, repelled by the negative plate. So this electron will bend down. If we had a positively charged particle, that would bend up in this electric field. So if we wanted to work out the acceleration in this vertical direction, because the acceleration will be in the same direction of the field, we can do that. Firstly, we can work out the electric field strength. That is equal to delta E equals delta V on D. And then once we've worked out the electric field strength, then we can substitute the electric field strength into the A equals Q E on M formula. And we can then basically analyse, we know that that's the vertical acceleration. There's no acceleration in the horizontal direction. We can analyse the motion of that. And I will go through shortly an example where we analyse the motion of a charged particle in an electric field. If you read on in your notes in terms of the science understanding that goes on from here, it talks a lot about a cyclotron. A cyclotron relies on both electric fields and magnetic fields to accelerate charged particles. I'm going to talk about a cyclotron after we've talked about magnetic fields, because I think it makes more sense. We can talk about the way the whole thing works. So we're going to come back to that learning intention later on. Let's continue on, and I think we're going to do an example problem. So, what do we need to be able to do? What skills do we need to be able to show to be successful here? A charged particle moving at an angle to a uniform electric field experiences a force which affects both components of its velocity differently. The component of the velocity parallel to the electric field changes due to the electric force, and the component perpendicular to the field remains constant. So this is very much like gravity. The force only acts in one direction, the direction of the electric field. There's no force acting perpendicular to the field. Therefore, it's going to lead to the parabolic motion that we see under gravity. So I think the first one here is compare the motion of a projectile in the absence of air resistance with the motion of a charged particle in a uniform electric field. Both will experience parabolic motion because there is a force only in one direction. Solve problems for the motion of charged particles that enter a uniform electric field perpendicular to the field, which is what we're about to do. Solve problems for the motion of charged particles that enter a uniform electric field at an angle to the field where the displacement of the charged particle parallel to the field is zero. Let me just read that one again. Solve problems for the motion of charged particles that enters a uniform electric field at an angle to the field where the displacement of the charged particle parallel to the field is zero. That's quite a complex statement. I actually think by saying that the displacement parallel to the field is zero, that basically means a charge that would, so we've got an electric field here, that is a charge that would enter the field, goes up. So say we've got the negative plate here, if we put a positive charge into this field going straight up, it would be basically repelled by the positive, attracted by the negative, so it would slow down. So it would start up, slow down, and then it would come straight back down, which sounds just like when we have a projectile and we throw it vertically straight upwards. There'll be a force acting on it. If it was a projectile, it would be gravity. It will slow it, and then it will pull it back down. That is basically just all the usual equations of motion. Anyway, I've got a previous exam question here. Sorry, it's a little bit small and hard, but hopefully it's good enough to read. Let's work through this to finish this video off. An electron is fired horizontally into a uniform electric field in the vacuum between two oppositely charged parallel conducting plates as shown in the diagram below. The electron enters the field halfway between the plates with a speed of 2 times 10 to the 7 metres per second. The plates are 0.15 metres long and the uniform electric field has a magnitude of 4 times 10 to the 3 volts per metre. So we haven't been given a voltage that we need to work out an electric field strength. It's given us the electric field strength. We could actually rearrange that formula and work out what the voltage is. If we knew the distance between the plates, which I don't think we do, so we won't worry about that. We also know the velocity of the electron, so we could work out the kinetic energy, and therefore we could work out how much work would need to be done to accelerate an electron, and therefore we could work out the voltage of that electron. But again, I don't think the question asks us that, so we won't do that. But they are all possible things that we could do. Generally, we'd be given an energy and need to work out a velocity, or we'd be given a voltage and need to work out an electric field strength. Anyway, let's address the question that we have. Show that the time of flight of the electron through the uniform electric field is 7.14 times 10 to the minus 9 seconds. So remember, no force acts in the horizontal direction. So no force acts perpendicular to the field. By that, the field is going to be here looking something like, I won't put too many lines in. The field will be downwards because go from away from positive towards negative. No force in that. We know that the initial velocity is 2.1 times 10 to the minus 7 metres per second, and we know the length, so we can basically go V equals S over T. If we rearrange that, T equals S over V, which is equal to 0.150 divided by 2.1 times 10 to the 7, and that, if we put into the calculator, will be equal to 7.14 times 10 to the minus 9 seconds. So, part B. Show the magnitude of the vertical acceleration of the electron in the region between the plates is. So our formula here for acceleration is equal to QE on M. Must get into the habit of showing our substitution. Q is equal to 1.6 times 10 to the minus 19 times by an electric field strength of 4.00 times 10 to the, and I've written through it and I can't even read it now, 10 to the 3 divided by the mass of the electron, which is 9.11 times 10 to the minus 31 kilograms. We put that all into our calculator and we get 7.03 times 10 to the 14 meters per second. Remember, that is acceleration, so it's meters per second. Also, it says the magnitude, so we don't need to worry about working out the direction. And in part 3, calculate the vertical displacement of the electron as it leaves the field. Give your answer to the nearest millimetre. So here we have the normal equations of motion. We have a constant acceleration problem. We know the acceleration inside that field. We know how long it's in the field for, so we can work that all out. So this is a little bit harder, so I'd probably write down the information in the question. We know the initial vertical velocity. Oops, let's just write that a bit neater. The initial vertical velocity is equal to 0. When it enters, it's all horizontal velocity. We know the acceleration in the vertical direction from the last question is 7.03 times 10 to the 14. Note how they gave you that as a show that, so that if you didn't get the answer to that question, then you still had an opportunity to do the last part of the question. We know the time is equal to 7.14 times 10 to the minus 9 seconds. And we're being asked to work out the vertical displacement. So might use this space over here. The vertical displacement will be equal to the initial vertical velocity times time plus a half a/t squared, where that's the acceleration in the vertical direction. So this term here, the initial vertical velocity is equal to 0, so that whole term equals 0. We'll just take that out now. So then we have SV equals a half times 7.03 times 10 to the 14 times by 7.14 times 10 to the minus 9 squared. Be a little bit careful on the calculator with this one. Put that all in and we get an answer of 0.0179. 3 significant figures reasonable? Yep, we got 3 significant figures all through the question. So remember, that's in metres and the question wants to the nearest millimetre. So if we times that by 1,000, that gives us, times by 1,000 gives us 17.9 millimetres. So there is an example of a typical motion of a charged particle in an electric field question. And that's it for our motion of charged particles in electric fields. Motion of charged particles in electric fields flip lesson. Thanks for watching.